Right now, an invisible field is pressing against every atom in your body. You can't feel it, you can't see it, but without it, your body would explode outward at the speed of light in less than a second. Every electron, every quark, every building block of matter you're made of would fly apart instantly. That field is real. Scientists proved it. And today, we're going inside it. We'll cover the machine built 17 miles underground to hunt for it, the particle that lives for less than a blink of nothing, and the discovery that the universe itself might be sitting on a hair trigger. If you enjoy this, subscribe and hit like. We're just getting started. Prepare yourselves. We begin. Close your eyes for a second and squeeze your hand into a fist. That feels solid. It feels real. It feels like matter doing what matter does. But here is the truth that physics has confirmed beyond any doubt. Your fist is almost entirely empty space. Every atom in your hand has a nucleus sitting at its center. Around that nucleus, electrons orbit at a distance so enormous relative to the nucleus's size that if you blew a single atom up to the size of a football stadium, the nucleus would be a marble on the 50-yard line. The electrons would be dust specks circling the outer seats. Everything in between? Empty. So why does your fist feel solid? Why doesn't it pass straight through objects like a ghost walking through a wall? The answer involves one of the strangest discoveries in the history of science, and it starts with a field you've never heard of, one that fills every corner of the universe, never rests, and has been pressing against your atoms since the moment you were born. When two objects try to occupy the same space, the electrons in their atoms repel each other. Electric forces push back. That resistance is what you feel as hardness. But those electrons only have the ability to push back because they carry a specific amount of mass. And that mass, it came from somewhere. Here is where it gets strange. Particles are not born with mass the way you're born with a name. Mass is something they pick up. Something gives it to them. And the thing that gives it to them stretches across the entire universe, in every direction, through every void, through every wall, through you. Right now, as you listen to this, scientists call it the Higgs field, and for most of the 20th century, it was just a theory, a mathematical idea that explained things nothing else could explain. Then, after nearly 50 years of searching, physicists found its proof: one single particle. The smallest ripple the field can make. A particle so short-lived that it exists for a time so brief that no human measurement can directly capture it alive. Your body is almost completely empty. The tiny fraction that isn't empty is held together by forces and fields working at scales smaller than anything you can picture. And one of those fields, the Higgs field, is the reason mass exists at all. Take it away, and every particle you're made of immediately becomes weightless. Then massless particles do what massless particles always do. They fly away at the speed of light, instantly, in every direction. No atoms, no molecules, no you. The fact that you exist, that anything exists with weight and substance and the ability to sit still, is a direct consequence of a field that fills the universe and never ever turns off. And we are going to understand exactly how that works, one layer at a time. Every chapter from here goes deeper. Every answer opens a stranger question. The physics underneath your everyday world is wilder than most people ever realize. And the next question is the one that changes how you see everything. What actually is a particle? Because the answer is nothing like what you were taught in school. Forget everything you picture when you hear the word particle. Most people imagine something like a tiny marble, a little solid ball too small to see, bouncing around in space. That image feels logical. It feels like a smaller version of things we already understand. It is completely wrong. Modern physics discovered something far stranger. Every particle in the universe, every electron, every quark, every photon of light is a ripple. Specifically, it's a ripple in an invisible field that stretches across all of space. Think about a calm lake. The water is everywhere. When you throw a stone in, the surface disturbs. A wave moves outward. That wave is real. You can measure it. You can feel it if it reaches you. But the wave is not a separate object floating on top of the water. The wave is the water itself, moving in a specific pattern. Particles work the same way. Every type of particle has its own field filling the universe. Electrons have an electromagnetic field. Quarks have their own fields, and when enough energy concentrates at one point, the field in that region vibrates. That vibration is what we call a particle. A particle is a local tremor in a field that covers everything. This is the core idea behind quantum field theory, the most accurately tested scientific framework in human history. When physicists calculate predictions using this theory, they match real-world experiments to an accuracy equivalent to measuring the distance from New York to Los Angeles to within the width of a single human hair. So, when you hear about the Higgs boson, you are hearing about a ripple in the Higgs field. The boson is the field's smallest possible disturbance. You cannot have a smaller unit of Higgs field vibration. It is the minimum. One quantum of the Higgs field's energy. Here is what makes this idea so powerful. Fields are everywhere all the time, even in a total vacuum. Even in the deepest, most empty region of space imaginable, far from any galaxy. These fields exist at zero energy, sitting still, ready to vibrate if something disturbs them. The entire universe is soaked in overlapping invisible fields, each one responsible for a different type of particle. This also means something that sounds strange at first. When an electron travels across a room, it is not a marble flying through the air. It is a moving pattern of excitation in the electron field, a ripple rolling across an invisible surface that spans the cosmos. That electron has mass. It moves at a fraction of the speed of light. It can be stopped, measured, captured. And the reason it behaves that way, the reason it has mass at all, comes from how it interacts with one specific field, a field unlike any of the others. Every other field sits quietly at zero energy in empty space. They only activate when a particle is present. But one field refuses to sit at zero. One field keeps a constant non-zero value everywhere in the universe, even in the deepest vacuum. It never turns off. It never weakens. And that stubborn, always-on field is what makes the entire physical universe possible. What that field actually does to particles moving through it is the next piece of the puzzle, and it is stranger than almost anything else in science. Picture the universe as the ocean floor, and you are a deep-sea creature that has lived underwater your entire life. You have never experienced air. You have no idea the ocean exists. You just swim. You just move. The water is everywhere around you, always, and it never occurs to you to question it because you have never known anything different. That is your relationship with the Higgs field. The Higgs field fills every cubic inch of space in the observable universe. It passes through planets, through stars, through the walls of buildings, through your skin, through the space between your atoms. It saturates everything. And unlike almost every other field in physics, it never sits at zero. Every other quantum field behaves like a flat, calm surface in empty space. No energy, no activity, just waiting. The Higgs field is different. Even in perfect absolute vacuum, it hums at a constant non-zero value. It is always active, always on, always interacting with whatever moves through it. Physicists describe this using a concept called the vacuum expectation value. Most fields have a vacuum expectation value of 0. That means in empty space they do nothing. The Higgs field has a vacuum expectation value greater than 0. In simple terms, even nothing is full of it. This is not a poetic description. It is a measurable, confirmed physical reality. The field does not have a location. You cannot point to where it is because it is everywhere equally. It does not come from a source the way light comes from a bulb. It simply exists as a permanent feature of the universe itself, woven into space the same way length, width, and height are. Now imagine walking through that ocean. A creature with no mass would glide through it effortlessly, completely unaffected. But a creature with mass would feel resistance. The water pushes back. The heavier the creature, the more the ocean slows it down. The Higgs field works exactly that way. Elementary particles move through it constantly. How strongly a particle interacts with the field determines how much resistance it experiences. That resistance is what we measure as mass. A particle that barely notices the field slips through almost freely and ends up with very little mass. A particle that interacts powerfully with the field struggles to move through it and ends up extremely heavy. And a particle that doesn't interact with the field at all feels nothing, gets no resistance, and ends up with zero mass. This is one of the most important ideas in all of physics. Mass is not a property that particles carry around with them from birth. Mass is the result of a continuous, ongoing interaction with a field that fills all of space. Right now, as you listen to this, every particle in your body is interacting with the Higgs field. Every electron, every quark inside every proton and neutron in every atom in your entire body is being slowed, being shaped, being given the property of mass by a field that permeates the universe. And here is the part that should make your stomach drop. The field does this universally. It does not pick favorites. It applies the same rules to every particle of the same type everywhere in the universe, which means the mass of an electron on Earth is identical to the mass of an electron in a galaxy 3 billion light-years away. The universe runs on one consistent set of rules, and the Higgs field is one of the referees. But why does the field stay on? Why doesn't it just collapse to zero like every other field in a vacuum? That answer changes everything. Every other field in the universe settles at zero when nothing is disturbing it. Think of it like a ball sitting at the bottom of a bowl. Gravity pulls the ball toward the lowest point. In empty space, other quantum fields naturally relax to their lowest energy state, which is zero. They sit still. They wait. That is their ground state. The Higgs field refused to do that. Its energy landscape does not look like a simple bowl with one low point at zero. It looks more like the bottom of a wine bottle. There is a raised bump in the very center, right at zero, and a circular groove running around it at a lower energy level. The field rolls away from zero and settles into that groove. That groove is its true lowest energy state. This is called spontaneous symmetry breaking, and it happened once, long ago, in the very first moments after the universe was born. Here is what that means in plain language. The Higgs field, when the universe cooled enough, rolled away from zero and locked into a stable non-zero value. It found its comfortable position, the actual bottom of its energy landscape, and it has stayed there ever since. Disturbing it away from that position requires enormous energy, so it stays put. It never turns off. Scientists call this the field's ground state, and it is not zero. It is a specific non-zero number that physicists have measured with precision. That number is baked into the structure of reality the same way the speed of light is baked in. Here is why this should feel strange. Zero is the calm. Zero is the empty. Every other field in the universe considers zero to be home. The Higgs field considers zero to be unstable. To the Higgs field, zero is the top of a hill, and it will always roll back down to its groove if you try to push it there. This means that every single point in the universe, including the emptiest void in deep space, contains a non-zero Higgs field. There is no place in the observable universe where the Higgs field is absent. There is no switch that turns it off. There is no region where particles can escape its influence. That permanence has consequences so large they are almost impossible to fully picture, because a universe where the Higgs field was zero, or where it could randomly turn off, would be a universe where mass does not exist. Electrons would have no mass. Quarks would have no mass. Atoms could not form. Stars could not exist. The universe would be a thin, uniform gas of massless particles flying around at the speed of light. spreading outward forever, never clumping, never building, never making anything. The fact that the field is locked permanently into a non-zero state is the reason structure exists in the universe at all. And this stability is not something physicists take for granted. The exact value the field settled into is not arbitrary. It is precisely the value that allows atoms to be the size they are, chemistry to work the way it does, and life to be possible. Slightly different, and everything falls apart. Scientists have confirmed the field exists. They found its ripple, but there are questions about the field's stability that lead to something far more unsettling than most people realize. That comes later. First, we need to understand exactly what the field does to a particle moving through it, and the best way to picture it involves something you've probably complained about walking through. Imagine walking through chest-deep water. You can move, but every step takes effort. The water pushes back. Your legs have to work harder than they would in open air. You feel slow, heavy, resistant. The water is not physically gluing itself to you, but its presence changes how you move through space. Now imagine a field like that water, except it fills all of space, and different particles experience it differently based on their own properties. Some particles wade through it like you through chest-deep water. Others feel almost nothing, and a few slip through without touching a single drop. That is the Higgs field. And the resistance particles feel moving through it is what we experience as mass. When physicists first described this interaction, they needed an image to explain it to the public. A physicist named David Miller, in 1993, wrote an explanation using a crowd of physicists at a party. A famous scientist walks in, and everyone in the room clusters around them, slowing them down as they try to cross the room. An unknown person walks in, and the crowd ignores them, letting them cross quickly. The famous scientist is a heavy particle. The unknown person is a light one. The crowd is the Higgs field. That analogy stuck. It is imperfect, like all analogies, but it captures something real. The top quark is the most massive elementary particle we know of. Its mass is roughly as heavy as an atom of gold. That is extraordinary for a particle classified as a fundamental building block. The reason is that the top quark interacts with the Higgs field extremely strongly. The field grabs it hard. It resists. That resistance is measured as enormous mass. The electron, by contrast, interacts with the Higgs field about 300,000 times more weakly than the top quark. The field barely notices the electron as it passes through. So the electron ends up with a mass so small it is nearly nothing by comparison. And the photon, the particle of light, does not interact with the Higgs field at all. The field is invisible to it. The photon passes through without any drag. As a result, the photon has zero mass, and massless particles obey a specific rule of physics. They must travel at the maximum possible speed in the universe, the speed of light. This is why light travels at the speed it does. The photon cannot travel slower because it has no mass to slow it down. There is nothing for the Higgs field to grab. Every other elementary particle with mass is experiencing a constant ongoing interaction with the Higgs field at every moment of its existence. Mass is not stored inside the particle. Mass is what happens when the particle and the field interact. Stop that interaction, and the mass disappears. This makes mass less of a property and more of a relationship, a continuous real-time relationship between a particle and the field it moves through. The particle does not own its mass. The field lends it. And here is a question that follows directly from that. If the field gives electrons their mass, and electrons are what orbit atomic nuclei, what happens to atoms when the field is active versus when it isn't? The answer to that question reaches back to the very beginning of the universe, and it involves a moment so extreme, so violent, that nothing we experience today gives us any reference for it. A beam of light travels from the sun to the Earth in about 8 minutes. It covers roughly 93 million miles in that time, and it does it without slowing down even slightly. Light in a vacuum always travels at exactly the same speed, in every direction, in every part of the universe. Nothing we have ever found travels faster. That speed is not a coincidence, it is a direct consequence of what light is. Light is made of photons, and photons have zero mass. Every experiment ever conducted, every measurement ever taken, every prediction ever confirmed, points to the photon as a perfectly massless particle. And the reason that is true leads directly back to the Higgs field. The Higgs field fills all of space with a constant non-zero value. It interacts with particles as they move through it. Those interactions are what generate mass. But the interaction only happens if the particle has what physicists call the right coupling to the field. Think of it as a compatibility. Some particles are built to interact with the Higgs field, others simply aren't. The photon is not compatible. It carries no electrical charge in the way that would allow a coupling to the Higgs field. The photon moves through the field, and the field does not respond to it. No interaction, no drag, no resistance. And because physics has one unbreakable rule, any particle with zero mass must always travel at the speed of light. That is not optional. A massless particle cannot travel slower. It has nothing to slow it down. No mass means no inertia. No inertia means no resistance to instant acceleration up to the maximum speed the universe permits. So light travels at the speed of light because the Higgs field ignores it. Now flip this around. What does this tell us about particles that do have mass? Every particle with mass, the electron, the quarks, the muon, they are all being perpetually slowed by their interaction with the Higgs field. They cannot reach the speed of light because the field keeps grabbing at them. The heavier the particle, the stronger the grab, and the more it resists being pushed to high speeds. Here is the part that should reframe how you see matter. The solidity of the world, the fact that things have inertia, the fact that you feel resistance when you push on a wall, all of that traces back to the Higgs field, constantly slowing particles down. Without it, every electron in every atom of every object would move at the speed of light. Electrons moving at that speed cannot orbit nuclei in stable paths. Atoms fall apart. Chemistry stops. Everything dissolves. The Higgs field, by giving particles mass, is what makes stability possible. It is what allows matter to slow down, gather, and build structures across billions of years. But if every particle gets a different amount of mass depending on how strongly it interacts with the field, then something must decide the strength of those interactions. Different particles get wildly different masses. The top quark is almost 350,000 times heavier than the electron. Why? What sets those interaction strengths? That question reaches into a part of physics that nobody has fully answered yet. And the contrast between the heaviest and lightest particles gives us one of the biggest unsolved puzzles in all of science. Two particles, both elementary, both fundamental building blocks of matter. One is nearly 350,000 times heavier than the other. No one fully understands why. The top quark and the electron are both elementary particles, meaning physicists have found no smaller pieces inside either of them. They are both interacting with the same Higgs field. They are both following the same laws of physics, but their masses are so wildly different that they might as well exist in separate universes. The electron has one of the smallest masses of any particle with mass. It's so light that it takes roughly 1,800 electrons to match the mass of a single proton, which is itself made of quarks. The electron barely registers in the Higgs field. It drifts through with almost no resistance. The top quark, on the other hand, has a mass roughly equal to an atom of gold. Gold, one of the heaviest common metals you can hold. A single fundamental particle, with no internal structure, carrying the mass equivalent of an entire heavy atom. The top quark interacts with the Higgs field so powerfully that it experiences more drag than any other known elementary particle. And here is the deepest mystery in that gap. Physicists know the outcome. They can measure both masses with extraordinary precision. But the standard model, the best theory of particle physics ever built, does not explain why the interaction strengths are what they are. The model accepts them as inputs. You plug in the numbers you measure, and the theory works beautifully. But it cannot derive those numbers from first principles. It cannot explain why the top quark couples to the Higgs field at the exact strength it does, or why the electron couples so weakly. This gap in understanding is called the flavor problem, or sometimes the Yukawa coupling problem, named after the mathematical terms that describe the interaction strengths. Physicists have several competing theories about what might explain it. Some involve extra dimensions curled up at scales too small to see. Some involve patterns in the math that nobody has cracked yet. None has been confirmed. What we know for certain, the Higgs field affects every particle differently, and the range of effects is enormous. From the near massless neutrinos to the crushingly heavy top quark, the Higgs field sorts particles into a spectrum of masses that spans many orders of magnitude. That sorting matters enormously for the universe we live in. If electrons were much heavier, they could not orbit atomic nuclei at the distances they do. Chemistry would break down. If quarks had different masses, protons and neutrons would be unstable. The universe would never have built the atoms we are made of. The specific pattern of masses the Higgs field assigns to particles is not random noise. It appears finely tuned for a universe that can build complex structures. Change any of those couplings significantly, and the periodic table collapses. The fact that we exist to notice the pattern is extraordinary. And the top quark has one more remarkable property tied to its enormous mass. It is so heavy, so strongly coupled to the Higgs field, that it decays almost instantly. It lives for less than a trillionth of a second. The Higgs field gives it enormous mass, and that enormous mass makes it one of the most unstable particles ever detected. There is a direct relationship between mass and instability, and it connects straight to the Higgs boson itself, the most unstable particle ever confirmed. You have been told your whole life that mass is how much matter something contains. That is not wrong, but it is incomplete in a way that changes everything. In everyday life, mass means weight. Heavy things have more mass. Lighter things have less. A textbook tells you mass is a measure of an object's resistance to being pushed around. Its inertia. Push a bowling ball and it resists. Push a tennis ball and it moves easily. The bowling ball has more mass. All of that is true and useful for describing the world we see. But it doesn't explain where mass comes from. Physics goes one level deeper, and at that level, mass looks completely different. For elementary particles, mass is the result of how strongly a particle couples to the Higgs field as it moves through space. The particle does not carry mass like a backpack. The mass emerges from an ongoing relationship between the particle and the field surrounding it. Here is a way to picture it. Think of a guitar string. The string has no sound on its own. Sound emerges when you pluck it, when it vibrates in air, when the motion of the string interacts with the medium around it. The sound is real, you can measure it, record it, feel it, but it exists because of the interaction between string and air. Mass works similarly for elementary particles. The particle interacts with the Higgs field. The field resists the particle's movement. That resistance is what we measure and call mass. The mass is real. You can feel it. Your entire body is made of it. But it emerges from interaction rather than from some internal store of heaviness inside the particle. This reframing has deep consequences. If mass is a product of interaction rather than an intrinsic property, then mass is context-dependent in a way that feels unsettling. Remove the Higgs field and mass vanishes. The particle does not become lighter. It becomes massless, instantly. A massless electron would immediately accelerate to the speed of light. An electron moving at the speed of light cannot be captured in an orbit around a nucleus. Without orbital electrons, atoms cannot exist. Without atoms, molecules cannot form. Without chemistry, biology is impossible. The entire tower of complexity that produced stars, planets, oceans, life, and you collapses back to the very first step. And that first step is the Higgs field granting mass to electrons and quarks. Here is another layer that surprises most people. Compound particles like protons are made of quarks held together by the strong nuclear force. The mass of those quarks, given by the Higgs field, accounts for roughly 1% of the proton's total mass. The other 99% comes from the energy of the quarks moving around inside the proton and the energy stored in the force binding them together. So when someone asks how much of your body's mass comes from the Higgs field, the honest answer is about 1%. The other 99% of your mass is binding energy from the strong nuclear force inside your protons and neutrons. 1% might sound small, but without that 1%, the remaining 99 disappears too. The structure only holds together because the pieces have mass, and the pieces only have mass because of the field. That 1% is the foundation, and to understand how it got there, you have to go back to the single most violent event in the history of the universe. Go back far enough, and none of this existed. No mass, no atoms, no structure, just raw energy flying in every direction at the speed of light. The universe did not begin with stars or galaxies or clouds of gas. It began as an unimaginably hot, dense point of energy, smaller than any scale we have words for, where the temperature was so extreme that the laws of physics as we know them could not fully operate. The Big Bang did not just create matter, it created the conditions for matter to eventually become possible. In the very first sliver of time after the Big Bang, something critical was missing. The Higgs field was not yet switched on. That statement sounds small, its consequences are enormous. Without the Higgs field active, every elementary particle had zero mass. Every electron, every quark, every fundamental building block of matter was massless. And massless particles obey one rule without exception. They travel at the speed of light. Picture a universe filled wall to wall with particles, all moving at the speed of light in every direction. Nothing slows down, nothing stops, nothing orbits anything else. Everything scatters endlessly outward. There is no mechanism to form anything, because forming a structure requires particles that can slow down, come close, and hold together. Atoms require electrons that can settle into orbits at specific distances from a nucleus. Orbiting requires moving at speeds far below the speed of light. Massless electrons cannot do that. They blast past nuclei without slowing, without capturing, without bonding. So in those first instants, the universe was extraordinarily simple and extraordinarily chaotic at the same time. Pure energy in every form, filling space, but unable to build anything. The temperature at that moment was so high that physicists believe the Higgs field existed in a different phase. Think of water turning to steam. Steam and water are both made of the same molecules, but they behave completely differently because of their energy state. In the extreme heat of the early universe, the Higgs field was in its high energy phase. Its value sat at zero. The field was there, but it was not active in the way it is today. This is a critical detail. The field did not appear later. It was present from the very beginning, but the conditions of the early universe prevented it from doing what it does now. For a fraction of a nanosecond, the universe was a perfect storm of massless particles. Every quark, every electron, every neutrino, all weightless, all flying, none of them capable of sitting still or building anything. And then the universe cooled, just a tiny drop in temperature from one extreme to a slightly less extreme. But that drop was enough to trigger something that permanently altered every particle in existence and set the entire course of cosmic history. The Higgs field was about to do something it has never undone since. It happened in less time than you could ever measure. A fraction of a nanosecond after the Big Bang, as the newborn universe expanded and its temperature dropped past a critical threshold, the Higgs field did something no other field had done. It changed state. It transitioned, and in doing so, it handed mass to every elementary particle in existence. Physicists call this a phase transition, the same word used for water freezing into ice. When water freezes, the molecules don't disappear or transform into something new. They rearrange. They settle into a fixed structure that changes everything about how the material behaves. The molecules are the same. The rules of their interaction change completely. The Higgs field did something analogous, but at a cosmic scale. Before the transition, the field sat at zero. The universe was in a symmetrical high-energy state where mass did not exist. After the transition, the field shifted to a stable non-zero value and locked there. That locking broke the symmetry, and the moment it did, every particle that had any coupling to the field instantly acquired mass. One moment the electron was massless, flying at the speed of light. The next moment the field had switched on around it, and the electron had mass, a specific fixed mass, the same mass every electron in the universe carries to this day. The same thing happened to every quark simultaneously. Every particle with a Higgs field coupling suddenly felt resistance, suddenly had weight, suddenly could slow down, and slowing down was everything. Particles that could slow down could fall toward each other under gravity. They could be captured. They could orbit. Quarks that had been flying freely could now be pulled together by the strong nuclear force and held in place to form protons and neutrons. Electrons that could slow down could eventually settle into stable orbits around atomic nuclei. Atoms became possible. From atoms came molecules. From molecules came chemistry. From chemistry came stars, planets, oceans, and, eventually, biology. Every single one of those steps was unlocked by the Higgs field phase transition in the first fraction of a nanosecond of existence. Here is something that scientists are careful to point out. This phase transition is not like flipping a light switch in a simple on-off sense. The field settling into its new state involved quantum processes that physicists are still studying. The exact dynamics of how the transition unfolded are a subject of active research. What is not in doubt is the outcome. The field locked into a non-zero value and has remained there ever since. The frozen state of the Higgs field is the foundation of the physical universe we inhabit. You are made of atoms. Atoms are possible because particles have mass. Particles have mass because the Higgs field made a phase transition about 13.8 billion years ago and never reversed it. That transition set a clock ticking. From that moment forward, chemistry was possible. Life was possible. But the particles that gained mass from that transition did something remarkable with it. They came together and built something the universe had never seen before, the first atoms. And understanding how that happened requires understanding why mass is what allows structure to exist at all. An atom is not complicated to describe. A nucleus sits in the center, made of protons and neutrons packed tightly together. Electrons surround it, moving in specific patterns at specific distances, forming what scientists call the whole thing is held together by electric force pulling the negatively charged electrons toward the positively charged nucleus. Simple enough, but every single piece of that picture depends on mass. Start with the electrons. For an electron to orbit a nucleus, it has to travel at the right speed at the right distance. Too fast and it flies away. Too slow and it spirals in and crashes. The correct orbital speed is determined by the electron's mass. Change the mass, and the orbital radius changes. Change it enough, and stable orbits become impossible. Before the Higgs field activated, electrons had zero mass. A massless electron cannot orbit. It moves at the speed of light. At that speed, the electric attraction from the nucleus cannot curve its path into a closed orbit. The electron blows straight past the nucleus without capturing. This is not a minor technical detail. It is an absolute barrier. Massless electrons cannot form atoms. Full stop. When the Higgs field switched on and gave electrons their specific mass, everything changed. Electrons gained inertia. They could now be steered. The electric force from the nucleus could curve their paths. Stable orbits became possible for the first time. But stable orbits alone don't make chemistry. Chemistry requires that electrons sit in very specific energy levels and interact with other atoms in predictable ways. Those energy levels are determined by the electron's mass, the strength of the electric force, and quantum rules about how waves behave in confined spaces. Change the electron's mass, and those energy levels shift. Shift them enough, and atoms stop bonding the way they need to for molecules to form. The specific mass the Higgs field gave the electron is not arbitrary. It is one of the values that allows chemistry to exist. Now look at the quarks inside the nucleus. Quarks have mass too, granted by the Higgs field. But as covered before, the quark masses themselves account for only a small fraction of the proton's total mass. The rest comes from the strong nuclear force energy inside the proton. But here is what the quark masses do control: the stability of the proton itself. The mass difference between the two lightest types of quarks, the up quark and the down quark, determines whether a free neutron decays into a proton or vice versa. That balance is critical for nuclear stability. Tip it significantly in either direction, and protons become unstable. Unstable protons mean no atoms. No atoms means nothing. The Higgs field did not just turn on mass for one particle, it tuned the masses of every elementary particle simultaneously to specific values. Those values happened to be compatible with atomic stability, chemical bonding, and eventually biological complexity. Scientists have run calculations testing what happens when you change the masses of quarks and electrons slightly. Small changes lead to universes with no atoms, no chemistry, or no stable matter of any kind. The Higgs field did not just unlock the universe, it unlocked a very specific kind of universe, one capable of enormous complexity. And yet, here is the twist that surprises almost everyone. The Higgs field is responsible for only a tiny fraction of the mass you feel when you lift your hand. The rest of your mass comes from somewhere else entirely, somewhere far more violent. You have heard the Higgs field described as the thing that gives mass to everything. That description is both true and deeply misleading. The Higgs field gives mass to elementary particles, electrons, quarks, muons, the fundamental building blocks. That is real and confirmed. But the moment you look at anything larger than an elementary particle, the Higgs field's direct contribution becomes surprisingly small. Take a proton. A proton is made of 3 quarks held together by the strong nuclear force. The Higgs field gives each quark a mass. If you add up the masses of those 3 quarks, you get a number that is roughly 1% of the total mass of the proton. The other 99% comes from something else. Inside the proton, the quarks are not sitting still. They are in constant violent motion, moving at speeds approaching the speed of light within the tiny space of the proton. They exchange particles called gluons constantly, the carriers of the strong nuclear force. This motion and this force storage create enormous binding energy. And energy has mass, as described by the most famous equation in physics. Energy equals mass times the speed of light, squared. The binding energy of the quarks inside the proton is massive, literally. It contributes about 99% of the proton's mass, with the quark masses from the Higgs field providing only the remaining 1%. Now extend this to your body. Your body is made of atoms. Atoms are made of protons, neutrons, and electrons. The electrons are very light, so the overwhelming majority of your body's mass is in the protons and neutrons. And as just established, about 99% of proton and neutron mass comes from strong force binding energy. So roughly 99% of the mass of your body comes from the energy of the strong nuclear force trapped inside protons and neutrons. The Higgs field provides about 1%. Here is the important clarification that 1% matters completely. Without Higgs-given quark masses, the quarks inside the proton would have no mass at all, and the binding energy calculations that produce the proton's bulk mass would collapse into a different result. The structure of the proton itself depends on the quark masses existing. The Higgs field's contribution is the foundation that makes everything else possible. Small in percentage, essential in function. It's like asking how much of a skyscraper is just the foundation. The foundation is a small fraction of the total structure, but without it, none of the rest stands. This distinction matters because it corrects a common misconception. When people say the Higgs field is responsible for all mass, they are describing its role as the root cause, the enabling mechanism. When scientists want to be precise, they acknowledge that most of the mass we experience day to day comes from energy stored in nuclear forces, with the Higgs field providing the crucial seed. The Higgs field is the smallest but most critical contributor to the mass of your body, and the particle that proves the field exists lived for such a short time that measuring it required building the largest machine humans have ever constructed. That machine is underground, 17 miles around, and it pushed physics to its absolute limit. Inside every proton in your body, a war is happening. 3 quarks are packed into a space about 100,000 times smaller than an atom. They should fly apart. They carry color charge, the strong force equivalent of electric charge, and the rules of physics say like charges repel. Yet, they stay together. The force holding them in that impossibly small space is the strongest force in nature by a significant margin. The strong nuclear force is what prevents your atoms from dissolving, and as a side effect of how extreme it is, it also generates the bulk of your body's mass. The mechanism works like this. Inside the proton, gluons constantly fly back and forth between the quarks. Gluons are the carriers of the strong force, the messengers that keep the quarks bound. But unlike photons carrying the electromagnetic force, gluons are remarkable because they interact with each other. Gluons carry the same color charge they transmit. They can create more gluons. The inside of a proton is a constant storm of quarks and gluons in furious motion. All of that motion is energy. All of that binding is stored energy. And energy has an equivalent mass, calculated by taking the energy and dividing by the speed of light squared. The sheer quantity of energy locked inside the proton by all this strong force activity is staggering. Add it up, and you get a proton with about 99 times more mass than the combined bare masses of its 3 quarks alone would suggest. The binding energy does the heavy lifting. This has a name: mass-energy equivalence. The famous equation that links them was published in 1905, but most people think of that equation in terms of bombs or reactors releasing energy. The flip side, energy being equivalent to mass, is what fills your body with weight. The energy of confinement, the furious motion of quarks trapped in an impossibly small space, becomes the mass you feel when you pick up your hand. Here is a visual to make this real. If you could somehow remove all the strong force energy from the protons and neutrons in your body and leave only the Higgs field mass of the individual quarks, your body's mass would drop to roughly 1% of what it is now. You would weigh about as much as a sheet of paper, roughly. The strong nuclear force built the bulk of you. The Higgs field built the quarks that the strong force works with. Both forces are essential, but they work at completely different scales and through completely different mechanisms. The Higgs field operates on individual particles. The strong force operates on their confinement inside larger particles. Together, they produce everything with weight in the observable universe. This also means that stars, planets, your chair, the ground beneath your feet, all made mostly of proton and neutron mass, are mostly mass created by the strong nuclear force. The Higgs field gave the quarks a starting mass. The strong force did the rest, and between those two mechanisms, every gram of ordinary matter in the universe got its weight. Understanding how both work together reveals something deeper. The universe has multiple layers of mass generation stacked on top of each other, and peeling back those layers led physicists to build something so extreme, so precisely engineered, that it deserves its own chapter. A field that fills the entire universe sounds impossible to study. You can't bottle it. You can't isolate a piece of it. You can't observe it directly the way you can observe a planet through a telescope. The Higgs field is invisible, structureless, everywhere at once. So how do you prove it exists? You disturb it. Every quantum field can be disturbed. When you put enough energy into a field, you create a ripple. That ripple is a particle. For the electromagnetic field, the ripple is a photon. For the electron field, the ripple is an electron. For the Higgs field, the ripple is the Higgs boson. The Higgs boson is the minimum possible disturbance of the Higgs field, the smallest unit of vibration the field can make. It carries no electrical charge, no color charge, and no quantum spin. Among all the particles in the Standard Model, those characteristics make it the simplest. Every other fundamental particle has at least one of those properties. The Higgs boson has none of them. Its mass is large, roughly 125 times the mass of a proton. That is heavier than most atoms. For a particle with no internal structure and no charge, that mass is unusual. It comes from the boson interacting with the very field it is a part of. The Higgs boson gives mass to itself through self-interaction with the Higgs field, a particle bootstrapping its own existence. That self-interaction is not circular logic, it is a prediction that falls directly out of the mathematics. The boson must have mass because the field it creates ripples in is a field that generates mass, so the boson, as a ripple of that field, also has mass. The boson also has the distinction of being the only fundamental scalar particle ever confirmed. Scalar is a physics term meaning it has no directional spin. All other fundamental particles have spin, a quantum property that makes them point or rotate in specific ways. The Higgs boson has zero spin. It is spherically neutral, in a way no other discovered particle is. This matters because spin determines how a particle interacts with other particles and fields. A particle with zero spin interacts in the most symmetrical way possible with everything around it. This is part of why the Higgs field affects all particles with mass equally based on their coupling, rather than favoring certain directions or orientations. The boson's existence was predicted in 1964 by several physicists working independently. The most famous name attached to the prediction is Peter Higgs, a quiet theoretical physicist at the University of Edinburgh, who published a paper describing the boson and the field as inseparable parts of the same mechanism. The paper was brief, the implications were enormous, and the physics community took note, because the boson completed a theory called the Standard Model, the best description of the fundamental particles and forces ever constructed. But predicting a particle and detecting it are completely different challenges. The Higgs boson, once disturbed into existence, survives for a time so short that describing it stretches language to its limit. How short? Compared to the Higgs boson's lifespan, the blink of an eye lasts an eternity. In 1993, a physicist named Leon Lederman wrote a book. Lederman was brilliant. He had won a Nobel Prize. He wanted to explain the Higgs boson to a general audience, to show why it mattered, why physicists were obsessed with finding it. He needed a catchy title for his book. He came up with one, The Goddamn Particle. His publisher refused it, too rough for a popular science book. So they landed on something more dramatic, The God Particle. The name launched into popular culture and never came back down. Newspapers loved it. Headlines ran it for years. Every major announcement about the Higgs boson used it. When the boson was finally discovered in 2012, the phrase God particle appeared in stories across every media outlet on Earth, and particle physicists hated every second of it. The problem is not sensitivity about the word God. The problem is that the nickname is scientifically backwards. The Higgs boson is not the most important particle. It is not the origin of everything. It does not create the universe or govern it from above. It is one particle among many, doing a specific job in a specific mechanism. Extraordinary, yes. Divine, no. Peter Higgs himself, the man whose name the boson carries, publicly stated that he disliked the nickname. He worried it gave the particle an inflated status that misrepresented what it actually does and how physics actually works. Other physicists were blunter in their criticism. Nobel laureate Leon Lederman's own co-authors considered the title an embarrassment to the field. The nickname also created a bizarre side effect. Because God particle sounds like a religious reference, the discovery was sometimes wrapped in a spiritual framing it never deserved. Media stories suggested scientists had found the source of all existence. Some religious figures weighed in on what the discovery meant for belief. None of that had anything to do with particle physics. What the Higgs boson actually does is a specific, measurable, testable function. It is the excitation of the Higgs field. Finding it confirmed that the field exists and operates as predicted. A remarkable achievement. A scientific triumph. A critical piece of humanity's understanding of reality. A god? No. Here is what the story of the nickname actually reveals. Science communication is hard. Explaining quantum field theory to a general audience requires translation. And translation, especially when filtered through publishers, editors, and headlines, sometimes distorts the original meaning beyond recognition. The fact that God particle became the dominant public label for the Higgs boson means that millions of people formed their first impression of one of the most important discoveries in physics history through a phrase that physicists find misleading. Lederman meant the book as a celebration of physics. The nickname became a distraction from the science itself. What the science actually says is this: the Higgs boson is a natural consequence of a field that follows mathematical rules. Those rules were written down decades before the particle was found, and the person who first wrote them down clearly enough to stake his scientific reputation on them did so in a quiet office in Edinburgh in 1964, and then waited nearly 50 years to see if he was right. That story is more remarkable than any nickname could capture. In the summer of 1964, Peter Higgs was a 35-year-old theoretical physicist at the University of Edinburgh. He was working on a problem that had been irritating physicists for years. The standard model of particle physics was taking shape. It was elegant, it was powerful, but it had a fatal flaw. The mathematics of the model required certain force-carrying particles to be massless. In reality, those particles had enormous mass. The math and reality disagreed. Something was generating mass that the equations didn't account for. Without an answer, the entire framework was broken. Higgs sat with the problem and proposed a solution. He imagined a new field, one that filled all of space with a non-zero value, one that interacted with particles and gave them mass through coupling. The field would break the symmetry the model assumed, and breaking that symmetry would allow the force-carrying particles to acquire mass while keeping the rest of the mathematics intact. The idea was elegant. The paper he submitted was 2 pages long. A quick note about the history. Several physicists, including François Englert and Robert Brout, published similar ideas independently around the same time in 1964. The mechanism was discovered in parallel by multiple groups, but Higgs was the first to explicitly predict that the field would have a detectable particle signature, a ripple that could in theory be observed in a collider. That prediction, combined with his name on one of the key papers, led to the boson carrying his name. The physics community recognized immediately that the idea was important, but proving it required finding the boson. And finding the boson required energies far beyond anything the colliders of the 1960s could produce. So the wait began. Higgs watched as accelerators grew more powerful through the 1970s, 80s, and 90s. He watched as physicists narrowed the possible mass range of the boson without finding it. He watched as the Large Electron-Positron Collider at CERN in the 1990s searched and came close but didn't see it. He watched the Tevatron at Fermilab narrow the search further. 40 years passed, then 45, then 48. By 2012, Higgs was 83 years old. He had spent half a century waiting for experimental confirmation of an idea he wrote down in 2 pages in 1964. The physics community had largely come to believe the boson existed based on indirect evidence and the internal consistency of the Standard Model. But belief is not discovery. And then an announcement was scheduled for July 4, 2012. Higgs was invited to CERN for it. He flew to Geneva. He sat in the auditorium with hundreds of other physicists and listened as 2 separate experimental teams, who had been searching independently using the same collider, presented their results. What they showed was the clearest evidence in history for the particle Higgs had predicted in 1964. He cried, an 83-year-old man in a crowded auditorium crying at a physics presentation. The machine that found it took decades to build and represents the peak of human engineering. And understanding what it does requires understanding what happens when protons collide at nearly the speed of light. Underneath the Swiss and French countryside, about 300 feet below the surface, there is a ring. The ring is 17 miles in circumference. Running through it is a tube kept at a vacuum more complete than the vacuum of outer space. The tube is surrounded by superconducting magnets, chilled to -456 degrees Fahrenheit, colder than the void between galaxies. The whole structure cost about $4.5 billion to build and took over a decade to complete. This is the Large Hadron Collider, and it was built for one primary purpose: to find the Higgs boson. The machine works by accelerating protons. Protons enter the ring and are pushed to extraordinary speeds using powerful electric fields. The superconducting magnets curve their path, bending them around the ring in tight circles. As the protons loop around, they gain energy with each circuit. By the time they are ready to collide, they are traveling at 99.9999% of the speed of light. At that speed, protons travel the entire 17-mile ring about 11,000 times every second. The collider runs 2 beams of protons simultaneously, traveling in opposite directions. At 4 specific points around the ring, the beams cross. When they cross, protons smash into each other head-on at energies so high that the collision briefly recreates conditions similar to those a fraction of a nanosecond after the Big Bang. Those collisions are violent beyond what everyday language can describe. Protons are not just particles bouncing off each other. They are dense packages of quarks and gluons moving at near-light speeds. When 2 protons collide at these energies, the quarks and gluons interact. Energy explodes outward, and the collision can produce particles that don't normally exist in the stable universe, including very rarely the Higgs boson. The word rarely is an understatement. For every 10 billion proton collisions inside the Large Hadron Collider, roughly 1 produces a Higgs boson. 10 billion collisions for one event. This is why the machine runs continuously, and why its detectors are the size of multi-story buildings. Around each collision point sits a detector, a layered machine made of millions of sensors designed to record every particle that flies outward from a collision. 2 of the major detectors, named Atlas and CMS, are each operated by teams of thousands of physicists from dozens of countries around the world. The scale of human collaboration required to find one particle is staggering. Scientists from over 100 countries speaking dozens of languages worked for years analyzing collision data, looking for the specific signature that a Higgs boson would leave behind. Because here is the challenge: the Higgs boson does not survive long enough to reach the detector. The moment it appears, it is already gone. What the detectors actually see is not the boson itself. They see the specific pattern of particles left after the boson decays. Identifying that pattern among billions of other collision products, confirming it as statistically real and not random noise, is one of the most demanding data analysis challenges ever undertaken. The machine that makes it possible is a marvel of engineering, and the physics that happens inside it, in a space smaller than a proton, at energies higher than anything on Earth, is where the Higgs boson vanished so fast. And what does vanish even mean for a particle? That answer involves a timescale so extreme that numbers alone can't capture it. Finding a particle that exists for less than a blink of nothing requires a machine that never blinks. Inside the Large Hadron Collider, the process of creating a Higgs boson begins long before any collision happens. Protons don't just appear in the ring. They start as ordinary hydrogen gas, the simplest atom in existence. Scientists strip the electrons away from hydrogen atoms, leaving bare protons. Those protons enter a series of smaller accelerators that act like a warm-up track, boosting their speed before they ever reach the main ring. By the time protons enter the 17-mile ring, they are already moving at a significant fraction of the speed of light. The main ring then pushes them further, using electric fields to accelerate them, and superconducting magnets to curve their path. The magnets are critical. At those speeds, a proton moving in a straight line would escape into the surrounding rock in an instant. The magnets bend the beam, keeping it circular, keeping the protons on track for thousands of laps. The beam is not a single proton. It is a stream of roughly 300 billion protons bunched together into packets. Two streams run simultaneously, one clockwise and one counterclockwise. They travel in separate vacuum tubes inside the same tunnel, moving in opposite directions, until they reach a collision point. At the collision point, the beams are focused to a width thinner than a human hair. Then they cross. Proton packets pass through each other. Most protons miss each other entirely. Space, even inside a proton beam, is mostly empty. But some collide. Each collision releases energy concentrated in a space smaller than a proton itself. The energy is so extreme that it can materialize new particles directly from pure energy, which is exactly what energy mass equivalence allows. Most collisions produce ordinary particles, pions, muons, jets of quarks, but extremely rarely the conditions are just right for the Higgs field to be disturbed enough to produce a boson. 1 in 10 billion collisions. That is the rate. The Large Hadron Collider compensates for that rarity by running at an almost incomprehensible pace. At peak operation, it produces roughly 1 billion proton collisions per second, 1 billion every second around the clock. Even at that rate, you only get about 100 Higgs bosons per second across the entire collider. Each of those bosons vanishes in a time too brief to describe in human terms. But before it vanishes, it decays into a specific set of lighter particles. The decay products fly outward and hit the detector. The detector records their paths, their energies, their identities. Then the data pours in. The amount of data generated by the collider's detectors is staggering, roughly 15 petabytes of data per year. 15 million gigabytes. A global network of computing centers processes this data continuously, searching for patterns buried inside billions of ordinary collision events. Physicists look for a peak. In the data, if a Higgs boson exists at a specific mass, the decay products will appear more often at the energies corresponding to that mass than random chance would predict. Over millions of events, that excess builds into a signal, a bump in a graph. A bump that changed physics. And getting to that bump required one of the most precise acts of engineering in human history. The machine that made it possible almost didn't work. The Higgs boson exists for a length of time that has no comparison in everyday life. 1/millionth of a billionth of a second. Written out, that is a decimal point followed by 21 zeros, and then a 1. The boson is born from the collision and gone before any conceivable physical process can interact with it. By the time the decay products reach the first layer of the detector, the boson itself has been gone for an eternity at its own timescale. To put that in perspective, the time between the boson appearing and disappearing is shorter, relative to 1 second, than 1 second is relative to the age of the universe. Stacked on top of itself billions and billions of times, the boson's entire lifespan still doesn't add up to anything a human could perceive. Why does it die so fast? The reason is its enormous mass. There is a direct relationship in quantum mechanics between how heavy a particle is and how quickly it decays. Heavy particles have many possible decay paths available to them. The laws of physics allow a heavy particle to break apart into combinations of lighter particles, releasing the mass energy as kinetic energy in the products. The more decay paths available, the faster the particle falls apart. The Higgs boson has more mass than most particles and couples to other massive particles strongly. That means it has several decay channels open. It can decay into 2 bottom quarks, 2 tau particles, 2 photons, 2 Z bosons, or other combinations. Each channel is a different way for the boson to vanish. With that many exits available, the boson doesn't last long. The decay into 2 photons is particularly important for detection. Photons are clean, easy to track, and carry precise energy. When physicists search for the Higgs boson in collision data, one of the clearest signals they look for is 2 high-energy photons appearing simultaneously from the same collision point. 2 photons with a combined energy equivalent to 125 proton masses. That specific signature stood out from the background noise and helped confirm the discovery. It is deeply strange that a particle associated with giving mass to others decays most cleanly into 2 photons, which are themselves massless. The boson doesn't couple to photons directly, so the decay happens through an intermediate step involving heavy particles called top quarks and W bosons that briefly appear and disappear in the calculation. The photons come out the other side. The entire chain of events, boson created, boson decays, photons decayed, happens so fast that the collider detectors don't even record the boson itself. They record only the aftermath. Scientists detect a particle they never directly see. They confirm its existence entirely through the pattern of what it leaves behind. This is a remarkable statement about the nature of scientific knowledge. Humanity built a machine 17 miles around, ran it for years, analyzed billions of collisions, and found a particle by reading its ghost. The boson was always invisible, its effects were real and measurable, and the moment those effects were measured precisely enough to be certain, the announcement came. A date was set, an auditorium was prepared, and one of the physicists invited to witness the result was an 83-year-old man who had been waiting since 1964. A particle that lives for a millionth of a billionth of a billionth of a second cannot be photographed. It cannot be trapped. It cannot be slowed down and examined. By the time any physical measurement could interact with it, the Higgs boson is already gone. Physicists had to develop an entirely different approach to detection, one based on reading what the boson leaves behind, rather than observing the boson itself. The ATLAS and CMS detectors, the 2 main instruments at the Large Hadron Collider, are each enormous. ATLAS is about 150 feet long and 80 feet wide. CMS is more compact but denser, weighing about 14,000 tons. Both are built from layered systems, each layer designed to catch and identify different types of particles produced in collisions. The innermost layer, closest to the collision point, tracks the paths of charged particles. When a charged particle moves through material, it ionizes atoms as it passes. The detector picks up these ionization signals and reconstructs the particle's trajectory. By bending the paths of charged particles using powerful magnetic fields and measuring the degree of curvature, physicists can calculate the particle's momentum. The next layers are calorimeters, devices that stop particles and measure their total energy. An electromagnetic calorimeter catches electrons and photons. A hadronic calorimeter catches heavier particles made of quarks. The energy deposited in each calorimeter tells physicists how much energy the particle carried. The outermost layer catches muons, heavy cousins of the electron that pass through all the inner layers without stopping. Muons leave clean tracks that are easy to identify. From all these signals together, the detector software reconstructs what happened at the collision point. It figures out which particles appeared, in which directions they flew, and how much energy each one carried. This reconstruction happens for every single collision, millions of times per second. For the Higgs boson, physicists looked for specific combinations of final particles that match known decay patterns: 2 photons of specific energies, 4 leptons in a distinctive arrangement. The signal of the Higgs boson is a bump, a slight excess of events at a specific energy value that appears more often than random collisions would produce. The bump is subtle. Extracting it requires enormous statistics. Billions of events must be collected and analyzed before the signal rises clearly above the background noise. Physicists use a statistical threshold called 5 sigma, meaning the excess must be large enough that there is less than a 1 in 3.5 million chance it appeared by random fluctuation. Reaching 5 sigma for the Higgs boson took years of data collection and analysis by thousands of physicists working across the global computing network. When the signal finally crossed that threshold in both the ATLAS and CMS detectors independently, it was checked and rechecked. The same bump appeared in both detectors at the same mass. 2 separate experiments run by 2 separate teams who deliberately kept their analyses independent from each other found the same particle in the same place. That double confirmation was the scientific gold standard. One detector could be a fluke. 2 independent detectors agreeing eliminated that possibility. The announcement could be made, the date was set, and the physics world prepared for something it hadn't experienced in a generation: the discovery of a genuinely new fundamental particle. The date was chosen deliberately. July 4th is American Independence Day. For physicists at CERN, the European Particle Physics Laboratory on the border of Switzerland and France, the date carried a different kind of significance. It was the day 2 teams of scientists, after years of rivalry and parallel work, would stand up and announce whether they had found the most sought-after particle in physics history. The auditorium at CERN filled early. Physicists who had spent years on the search flew in from around the world. Graduate students who had built their entire doctoral thesis around Higgs boson data crowded the hallways. People watched the live stream from labs in the United States, Japan, Russia, India, and dozens of other countries. The 2 collaborations, ATLAS and CMS, had deliberately kept their analysis separate. The teams had different physicists, different software, different methods. They were searching for the same signal without coordinating their results, so that if both found the same thing, it would be genuine independent confirmation rather than shared bias. The presentations began. CMS went first. The spokesperson for CMS walked through the data systematically. The collaboration had seen a clear excess of events at a mass of approximately 125 times the proton mass. The excess appeared in multiple decay channels simultaneously. The statistical significance was well above 5 sigma, an unmistakably real signal. Applause. Then ATLAS presented the same story, a clear signal at the same mass, the same level of statistical confidence. 2 independent experiments using 2 independent detectors built by 2 independent teams of thousands of physicists had found the same particle in the same place at the same mass. The room understood immediately what that meant. Then the CERN Director General stood and said clearly that they had reached a milestone in the understanding of nature, and that the new particle was consistent with the long-sought Higgs boson. The crowd responded with an ovation that lasted several minutes. Cameras caught Peter Higgs in his seat, visibly emotional. He turned to Francois Englert beside him. Englert, who had published his own version of the same idea in the same year, sat next to Higgs and watched the confirmation of their shared theoretical work, separated by 48 years from the day the idea was first written down. Outside the physics community, the news travelled fast. Major newspapers ran front-page stories. Television networks covered it. Even people with no physics background recognized that something historically significant had happened. The phrase "God particle" appeared in nearly every headline, to the continued frustration of physicists everywhere. Inside CERN, the reaction was quieter and more precise. Physicists celebrated the discovery while noting carefully that the new particle was consistent with the Higgs boson, but required further study to confirm all its properties matched predictions. Exactly. That careful language mattered. Science does not declare victory in a single moment. It accumulates precision. But for one day, the auditorium at CERN held something rare, a room full of people who had worked their entire careers toward a single question, and who had just watched that question receive its answer. The Nobel Committee was watching too. Peter Higgs was not someone who sought attention. Throughout his career, he published relatively few papers, avoided conferences when he could, and spent most of his time teaching rather than chasing discoveries. By the time the Large Hadron Collider was being built, he had already retired from the University of Edinburgh. He gave occasional interviews but was uncomfortable with the celebrity that his name attached to the boson had created. He had waited since 1964, 48 years. That gap between prediction and confirmation is the longest in the history of particle physics. It outlasted careers, institutions, and entire collider experiments. The machines built in the 1970s could not reach the necessary energy. The machines built in the 80s and 90s came close and narrowed the search, but found nothing definitive. The Tevatron at Fermilab in Illinois ran through the 2000s and chipped away at the possible mass range, but the Higgs remained just out of reach. Each time a collider fell short, Higgs waited. Each time a search found nothing and set new limits, Higgs waited. Friends and colleagues who had been young physicists when the idea was published grew old. Some did not live to see the discovery. When the Large Hadron Collider switched on in 2008, the physics community believed it finally had enough energy to reach the Higgs boson if the particle existed where the standard model suggested. The collider ran through 2010, 2011, 2012, accumulating data. By mid-2012, both the Atlas and CMS teams were sitting on data they had not yet fully analyzed. Higgs was invited to CERN for the announcement before the results were officially known. He traveled to Geneva, unsure of what he would hear, but aware that the moment was close. He sat in the auditorium. He watched the CMS presentation. He watched the Atlas presentation. He saw the bump in the data at 125 proton masses. He saw the 5 sigma confidence in both results. He understood what he was looking at. He cried. The man who proposed the field and the particle, who had spent nearly 5 decades being asked whether he was frustrated by the wait, whether he regretted not switching to a different problem, whether he thought the boson would ever be found, sat in a room and watched 48 years of uncertainty resolve into a clear signal on a graph. After the presentations, journalists asked him how he felt. He said it was really an incredible thing that had happened in his lifetime. He was not given to dramatic statements. That was as close as he got to expressing what the moment meant. 1 year later, the phone rang. On October 8th, 2013, Peter Higgs was sitting in a restaurant in Edinburgh, having lunch. He didn't have a cell phone, he wasn't checking the news. He had stepped out for a quiet meal. And while he sat there, the Royal Swedish Academy of Sciences announced in Stockholm that the Nobel Prize in Physics for 2013 was being awarded jointly to Peter Higgs and Francois Englert for their theoretical discoveries related to the mechanism that contributes to the understanding of the origin of mass of subatomic particles. A former colleague spotted Higgs on the street as he walked home and told him he had won. That was how one of the most anticipated Nobel Prizes in physics history reached the man it honored, through a neighbor on a sidewalk. Englert received the prize alongside Higgs. Englert had published his paper, co-authored with Robert Brout, weeks before Higgs in 1964. Brout had died in 2011, just over a year before the discovery at CERN. The Nobel Prize is not awarded posthumously, so Brout's foundational contribution to the same mechanism went unrecognized by the Nobel Committee. His absence from the ceremony was noted by many in the physics community. The prize recognized the theoretical prediction specifically, not the experimental discovery. The thousands of physicists at Atlas and CMS who built the detectors, ran the analysis, and found the actual signal received no individual Nobel recognition. That is a structural feature of how the Nobel Prize works. It goes to individuals, and the prize cannot be shared among more than 3 people in any given year. The limitation frustrated some in the community. Modern physics is a collaborative enterprise. The discovery of the Higgs boson involved more people than any individual award can encompass. Several prominent physicists openly discussed whether the Nobel structure was capable of properly honoring large-scale collaborative science. Higgs himself seemed mildly uncomfortable with the attention. He was pleased that the physics was recognized. He was characteristically modest about his personal role, pointing out that the mechanism bore his name largely due to historical convention rather than any claim to sole discovery. He traveled to Stockholm for the ceremony in December of 2013. He accepted the medal and the diploma. He gave a short speech. He thanked the experimentalists, and then he went home. The discovery itself did not end the physics. It opened a new chapter, because confirming the boson existed was the beginning of a much harder question. The Higgs boson had the mass the standard model could accommodate, but the math behind that mass contained a problem so serious that some physicists called it the most embarrassing puzzle in all of theoretical physics. The Higgs boson has a mass of about 125 times the proton's mass. That sounds significant, and it is. But according to the mathematics of quantum field theory, that number is wildly, almost offensively small. Here is the problem. In quantum field theory, every particle constantly interacts with every other particle through virtual processes. These are brief, invisible interactions that happen continuously in the quantum vacuum, the so-called empty space, that is actually buzzing with fleeting particle-antiparticle pairs appearing and vanishing. These virtual interactions affect the measured mass of the Higgs boson. When physicists calculate how much these virtual interactions should shift the Higgs boson's mass, the answer is catastrophic. The corrections should push the Higgs mass up to the Planck scale, the highest possible energy scale in physics, roughly 10 million times larger, 10 million billion times. That is the mismatch. For the Higgs boson to have its measured mass of 125 proton masses, something must be cancelling out those enormous corrections almost perfectly. The positive contributions and the negative contributions must balance to an extraordinary degree of precision. Imagine a seesaw with weights totaling 10 million billion pounds on each side, balanced so perfectly that the difference between the two sides is exactly 1 pound. That is the level of cancellation required. Physicists call this fine-tuning, and fine-tuning at that level feels deeply unnatural. In science, when an answer requires numbers to cancel almost perfectly with no apparent reason, it usually signals that something is missing from the theory. The theory is incomplete. This puzzle is called the hierarchy problem. Why is there such a vast gap between the measured mass of the Higgs boson and the scale at which quantum corrections should push it? Several proposed solutions exist. The most famous is supersymmetry, a theoretical framework that pairs every known particle with a heavier shadow partner. If supersymmetric particles exist, they would contribute corrections to the Higgs mass that cancel the standard corrections naturally, without requiring extreme fine-tuning. The cancellation would emerge automatically from the symmetry. The Large Hadron Collider searched extensively for supersymmetric particles during its first 2 major runs. It found none. That absence has not ruled out supersymmetry entirely, since supersymmetric particles could be heavier than the collider could reach. But the lack of discovery has deflated enthusiasm for supersymmetry as the solution. Other proposals involve extra dimensions of space, curled up at scales too small to observe directly. In these theories, gravity leaks into the extra dimensions and appears weak to us, which could naturally explain the hierarchy without fine-tuning. Again, no direct evidence has appeared. The hierarchy problem remains open. The Higgs boson has the mass it has. The math says it should be almost inconceivably heavier. Something prevents that. Nobody knows what. And the hierarchy problem is not the only unsettling thing about the Higgs boson's mass. The exact value measured puts the universe in a situation far stranger than simply having an unexplained number. It puts the entire universe on a razor's edge between two very different fates. And what hangs in the balance is whether reality itself is stable. Every particle you know might have a twin, a hidden partner, a shadow version sitting just beyond what current physics can reach. Heavier, invisible with current technology, but mathematically necessary to solve one of the biggest problems in physics. This idea is called supersymmetry, and it was one of the leading candidates to explain why the Higgs boson has the mass it does. Here is the core of the theory. In the standard model, particles come in two types. Fermions are matter particles. Quarks, electrons, neutrinos. Bosons are force-carrying particles. Photons, gluons, the W and Z bosons, and the Higgs boson. Supersymmetry proposes that every fermion has a boson partner, and every boson has a fermion partner, all with the same quantum numbers but different spin. The partner of the electron would be called the selectron, the partner of the quark would be the squark, the partner of the photon would be the photino, the partner of the Higgs boson would be the Higgsino. An entire shadow periodic table of particles, one partner for every particle already known. These partners have never been detected. The reason supersymmetry is still taken seriously, despite that absence, is mathematical. When you calculate the virtual corrections that push the Higgs boson's mass toward the Planck scale, the contributions come from fermions and bosons in opposite signs. Fermion loops contribute negative corrections. Boson loops contribute positive corrections. If every fermion has an exact boson partner, and vice versa, the corrections cancel naturally and completely. The Higgs mass stays light. No extreme fine-tuning required. The hierarchy problem dissolves. That automatic cancellation is elegant. It is the kind of elegance that physicists find compelling because nature has repeatedly rewarded elegant mathematics with real discoveries. The problem is that supersymmetric particles have to be heavier than their standard model partners, or they would have been detected long ago. The heavier they are, the less perfectly they cancel the Higgs mass corrections, and the more fine-tuning creeps back in. The Large Hadron Collider's first two major data runs searched for supersymmetric particles up to masses of several thousand proton masses, and found nothing. That null result was sobering for many theorists. It didn't kill supersymmetry. The particles could simply be heavier than the collider currently reaches, requiring higher energies to produce. But it pushed supersymmetry out of the comfortable mass range where it would have solved the hierarchy problem most elegantly. Several physicists have shifted their interest to other ideas. Some explore theories with no supersymmetry at all, accepting that fine-tuning might simply be a feature of our universe rather than evidence of missing physics. Others investigate clockwork mechanisms or relaxation models where a slow cosmological process naturally drove the Higgs mass to its current low value over the age of the universe. None of these alternatives has been confirmed. The hierarchy problem remains standing, supersymmetry remains unproven, and the Large Hadron Collider's third major run, which began in 2022 at record energies, is pushing the search further. Every collision is another data point. Every analyzed dataset narrows the possible hiding spots for new physics. The answer might come from the collider, or it might require a machine even larger and more powerful. Physics has already demonstrated it can wait decades for an answer. But there is another possibility that no mathematical fix can address. What if the Higgs boson is not a fundamental particle at all? The Higgs boson is classified as a fundamental particle. That means as far as current physics can detect, it has no internal structure, no smaller pieces inside, but history has a pattern of humbling that classification. Atoms were once considered fundamental. Then the nucleus was found inside them. The nucleus was considered fundamental. Then protons and neutrons were found inside it. Protons and neutrons were considered fundamental. Then quarks were found inside them. Every time physics declared something elementary, a deeper layer eventually appeared. Some physicists are skeptical that the Higgs boson will be the last exception to this pattern. They propose that the boson might actually be a composite particle, built from smaller, currently undetectable components, bound together by an entirely new force, operating at scales far smaller than anything current technology can probe. This class of ideas is called compositousness, or sometimes partial compositous models. The basic argument is this: the Higgs boson behaves oddly for a fundamental particle. Its mass is suspiciously light given what the quantum corrections say it should be. Its interactions with other particles follow specific patterns that could, in principle, be explained if it were a bound state of more fundamental constituents. If the Higgs boson is composite, then what looks like the Higgs field is actually an effective description of something more complex, operating at shorter distances. The field and the boson would be emergent phenomena, real and measurable at the scales we can access, but built from a deeper structure we haven't reached yet. This idea is not new. Before quarks were discovered, physicists proposed that the proliferation of strongly interacting particles in the 1950s and 60s suggested an underlying structure. They were right. The same logic applied to the Higgs boson could point toward a new layer of reality. One well-developed version of this idea involves particles called techniquarks, hypothetical particles bound together by a new force called technicolor. Techniquarks, binding into composite states, would produce a particle that looks exactly like the Higgs boson at current energy scales. At higher energies, the internal structure would become visible. The challenge is that composite Higgs models generally predict additional particles and new phenomena that the Large Hadron Collider should have seen by now. So far, none have appeared. Like supersymmetry, the idea remains viable but under pressure. Current measurements of the Higgs boson's properties show it behaving almost exactly as the standard model predicts for a fundamental particle. Its coupling strengths to other particles match predictions to within a few percent. Any significant deviation would signal something beyond the standard model, potentially pointing toward compositeness. The margin for deviation is shrinking with every new measurement. If the boson is composite, its internal structure must be hidden at energies significantly beyond what current experiments reach. What the Higgs boson is made of, at the deepest level, remains an open question, and the answer has implications that stretch far beyond particle physics into the structure of the universe itself. Because if the Higgs boson's properties shift even slightly from what the standard model predicts, it could change the calculation that determines whether the universe we live in is actually stable. The universe might be sitting in a hole that isn't quite the bottom. That sentence sounds abstract. What it describes is one of the most alarming implications of modern physics, and it follows directly from the measured mass of the Higgs boson. Think back to the wine bottle analogy from earlier. The Higgs field settled into a groove around the rim of the bottle after the Big Bang. That groove represents the field's lowest energy state. The field sits there, stable, and the universe runs on the physics that groove produces. But what if that groove is not the absolute lowest energy state? What if there is a deeper hole that the field hasn't fallen into yet? Physicists calculate the stability of the Higgs field by mapping out its energy landscape mathematically. The shape of that landscape depends on precise values of physical constants, especially the mass of the Higgs boson and the mass of the top quark. Plug in the ROM values, and the landscape changes shape. When scientists use the measured mass of the Higgs boson at approximately 125 proton masses and the measured mass of the top quark, the calculation produces an uncomfortable result. The universe appears to be in a metastable state. The field is sitting in a local minimum, a stable enough groove, but the absolute lowest energy state of the field exists somewhere else, at a different field value, lower and deeper. The field is trapped in a good enough position, a comfortable enough groove, one it has no immediate reason to leave, but one that is not the true bottom. This situation is comparable to a ball sitting in a small dip on the side of a hill. The ball is stable in that dip. Give it a small push and it rolls back, but give it a large enough push and it rolls over the edge of the dip, down the slope to the actual bottom of the hill. For the Higgs field, the push required to knock it out of its current state is enormous, far beyond anything happening in the universe today. Even the violence inside the Large Hadron Collider, the most energetic controlled collisions in human history, are nowhere near the energy required to destabilize the field globally. So the current situation is, the field is probably stable on any timescale relevant to human existence, civilizations, or even the long-term fate of the solar system. Probably. The calculation has uncertainties. The exact mass of the top quark is not known with perfect precision. Small shifts in its measured value push the stability calculation in one direction or another. Some measurements place the universe comfortably in a stable zone. Others, within the current measurement uncertainties, allow for a genuinely metastable scenario. Physicists are working to narrow those measurements with every new dataset from the Large Hadron Collider. The stakes of that calculation are extraordinary. Whether the universe is truly stable or sitting in a metastable state determines something that no other branch of science touches. Whether the laws of physics as we know them are permanent, or whether they could one day be replaced by something entirely different. The mechanism that would cause that replacement has a name, and understanding it requires picturing something that moves at the speed of light and leaves nothing recognizable in its wake. Somewhere in the universe, right now, a bubble might already exist. A bubble where the Higgs field has slipped from its current metastable groove into a lower energy state. A region of space where the value of the Higgs field is different, where the masses of elementary particles are different, where the rules of physics as we know them no longer apply. This bubble would be invisible, it would radiate no light, it would send no warning signal, and it would be expanding at the speed of light in every direction. This is vacuum decay. The mechanism works as follows. If the Higgs field is in a metastable state, quantum mechanics allows for a process called tunneling. Quantum tunneling is the phenomenon where a particle or field configuration can spontaneously shift through a barrier that classical physics says is impassable. It happens all the time at small scales. Electrons tunnel through barriers in transistors. Atomic nuclei tunnel during radioactive decay. For the Higgs field, tunneling would mean a small region of space spontaneously transitioning to the lower energy state. A tiny bubble, smaller than a proton, where the field value has jumped to its true minimum. That bubble would immediately begin to expand. The wall of the expanding bubble moves at the speed of light. Inside the bubble, physics is different. The Higgs field has a different value, which means elementary particles inside the bubble have different masses. Atoms as we know them cannot exist there. Chemistry as we know it cannot operate there. Every structure built from the current laws of physics dissolves as the bubble wall passes through it. The bubble does not slow down. It expands at the maximum speed the universe allows. Nothing can outrun it. No signal can precede it. If a vacuum decay bubble were heading toward Earth from 1,000,000 light-years away, it would arrive 1,000,000 years from now, and nothing in that 1,000,000 years would give any warning that it was coming. Here is the part that matters for the current situation. The probability of vacuum decay happening spontaneously anywhere in the observable universe during the current age of the universe is, based on current calculations, extraordinarily small, smaller than any probability a human would normally think about. The universe has existed for about 13.8 billion years without this happening, and the expected timescale before it would happen by chance, if the universe is indeed metastable, is vastly longer than the current age of the universe. Some physicists take comfort in that timescale. Others point out that extremely unlikely is not the same as impossible, and that the consequences of it happening are so absolute that even a small probability deserves attention. What would vacuum decay feel like if it happened nearby? That answer requires only a moment's thought, and it is the strangest and most absolute conclusion in all of physics. Nothing. You would feel absolutely nothing. The wall of a vacuum decay bubble travels at the speed of light. Light from the approaching bubble wall reaches you at the same time the bubble wall does. There is no advanced warning, no sound, no flash you could perceive in advance. The bubble wall and the light it could theoretically emit arrive simultaneously. One moment you exist, the next moment the bubble wall has passed through you. The passage takes no time you could experience. The physics inside the bubble is different enough that atoms cannot maintain their structure. The electron mass changes, the orbital energies change. Chemistry stops. Everything that exists by virtue of the current Higgs field value dissolves in the instant the wall passes. From outside the bubble looking in, an outside observer would see nothing either. The bubble wall absorbs no distinguishable light. The wall is simply the boundary between two regions of the universe with different physics. An observer watching from far outside would see a region of space suddenly go dark as all light-emitting processes inside ceased, and then the darkness would expand at the speed of light, erasing everything it touched. There would be no explosion in the traditional sense, no dramatic fireball, just an expanding boundary beyond which the old rules no longer apply. What makes this concept so unsettling is its totality. Every other threat physics or astronomy describes, asteroid impacts, supernovae, even the eventual death of the sun, leaves something. Vacuum decay leaves nothing. The matter and energy inside the bubble don't go somewhere else. They reorganize according to different rules that don't support the structures that allowed them to be anything recognizable. Some physicists argue that the new vacuum state inside the bubble might support its own kind of physics, its own potential for structure and complexity, just governed by different rules than ours. The masses would be different. The forces might be different. The periodicity of elements might not exist. Whether any kind of meaningful complexity could emerge from those different rules is completely unknown. What is known is that nothing currently existing, no molecule, no atom as we know it, no human, would survive the transition. There is also a version of this scenario that provides an odd kind of comfort. If the universe is truly stable, and the current Higgs field value is the absolute minimum, then vacuum decay is simply impossible. The field has no lower state to tunnel into. The energy landscape has no deeper hole. The universe runs forever on the current physics. Determining which scenario is real requires knowing the Higgs boson's mass and the top quark's mass with extraordinary precision. That measurement is exactly what the Large Hadron Collider's third major run, which began in 2200, is designed to refine. Every new data point from CERN is a step toward knowing whether the universe we live in is permanent or provisional. In April of 2022, the Large Hadron Collider powered back up. After 3 years of upgrades and improvements, it restarted at the highest collision energies ever achieved by any machine in human history. The previous runs had operated at energies of 7 and then 13 trillion electron volts. Run 3 pushed that to 13.6 trillion electron volts. A new record. The upgrades were not just about raw energy. Engineers improved the beam brightness, meaning more protons packed into each bunch, producing more collisions per second. New detectors were installed, computing infrastructure was upgraded to handle higher data rates. The machine that had already found the Higgs boson was rebuilt to study it in far greater detail. The primary scientific goals of Run 3 extend beyond simply finding the boson again. The focus now is precision measurement. Physicists want to know exactly how the Higgs boson behaves. How strongly does it couple to each type of particle? Does it match standard model predictions exactly? Or are there small deviations that hint at new physics hiding just beyond current reach? Those coupling measurements matter enormously. If the Higgs boson is truly a fundamental particle as the standard model describes, its couplings to other particles should follow a specific pattern with specific numerical values. Any deviation from those values, even a small one, would signal that something is wrong with the current theory. New particles or new forces could be distorting the couplings. Run 3 data from the ATLAS and CMS collaborations, released in 2026, provided the most precise measurements of the Higgs boson's mass ever achieved, pinning it at approximately 125 proton masses with unprecedented accuracy. Each new measurement tightens the constraints on what new physics could be hiding in the Higgs sector. The collider is also searching for new particles predicted by theories beyond the Standard Model. Every collision could produce something unexpected, an unknown particle decaying in a distinctive pattern, a new force carrier showing up in the data. The machine runs continuously, and the data flows to analysis centers around the world. The results, so far from Run 3, confirm the Standard Model with remarkable precision. The Higgs boson continues to behave almost exactly as predicted. Its couplings match expectations. Its mass is pinned tighter than ever. For some physicists, this consistency is reassuring. The Standard Model is extraordinarily accurate. For others, it is frustrating. If new physics exists at scales the Large Hadron Collider can reach, it is hiding extremely well. The search continues, and the physics community is already planning what comes next. Machines larger and more powerful than anything currently operating. The questions about the Higgs field are too important to leave unanswered. But the collider data has already revealed something remarkable about the boson itself, something that has no parallel in all of particle physics. The Higgs field has one specific value everywhere in the universe, a fixed, constant number baked into the structure of space itself. Everything about the physical world you experience depends on that number staying exactly where it is. The electron has the mass it has because the Higgs field couples to it at a specific strength. And the field sits at its current value. If the field's value were twice as large, the electron would be twice as heavy. If the electron were twice as heavy, electrons would orbit atomic nuclei at smaller radii. The energy levels of atoms would shift. Chemistry would produce different molecules. The periodic table would still exist, but the chemical reactions that build proteins, replicate DNA, and drive metabolism would all be different, possibly impossible. Life as it exists on Earth is calibrated to the specific field value the Higgs field settled into 13.8 billion years ago. Slightly decrease the field's value, and electrons become lighter. Lighter electrons orbit farther from nuclei. Atoms become larger, more diffuse, less able to bond in the tight specific geometries that complex molecules require. Chemistry again breaks down. The same sensitivity applies to quark masses. Change the Higgs field's value, and the mass difference between up quarks and down quarks shifts. That difference determines whether protons decay into neutrons or vice versa, which sets the ratio of hydrogen to helium in the universe, which determines how stars burn, how long they live, and what elements they produce. One field, one value, an entire chain of consequences stretching from fundamental particle physics all the way up to the existence of stars, planets, chemistry, and biology. Physicists call this kind of sensitivity fine-tuning. The universe appears to require very specific values for its fundamental constants in order to produce any meaningful complexity. The Higgs field value is one of the most critical of those constants. The question of why the field settled at its specific value rather than some other value connects to some of the deepest unsolved problems in physics. Some researchers invoke the anthropic principle, the observation that we can only exist in a universe compatible with our existence, so naturally we find ourselves in a universe with the right Higgs field value, even if other values are possible in some broader framework of universes. Others find that reasoning unsatisfying and look for a dynamical explanation, some mechanism, some symmetry, some physical process that would naturally drive the Higgs field to its current value, without requiring the universe to be fine-tuned by coincidence or selection. No such mechanism has been confirmed. What has been confirmed is that the value of the Higgs field is not arbitrary from the perspective of life. It is precisely what life requires, and changing it even modestly in either direction would produce a universe where complexity cannot exist. That extraordinary sensitivity is what makes the boson's self-interaction one of the most important properties physicists are currently trying to measure. Every other particle in the Standard Model acquires its mass by interacting with the Higgs field from outside. The electron couples to the field. The coupling produces resistance. The resistance is mass. The electron and the field are two separate things interacting with each other. The Higgs boson is different. The Higgs boson is itself a ripple of the Higgs field. It is made of the field. It does not interact with the Higgs field as an external object. It is the field locally vibrating. So how does the Higgs boson acquire its own mass? Through self-interaction. The boson couples to its own field. The field is everywhere, including at the location of the boson itself. The boson, as a disturbance of the field, interacts with the undisturbed field surrounding it. That interaction produces mass. A particle pulling itself up by its own bootstraps, generating mass from its own presence in the field it creates ripples in. This self-coupling is not just a philosophical curiosity. It has measurable physical consequences. The strength of the Higgs boson's self-interaction determines the exact shape of the Higgs field's energy landscape, the wine bottle shape described earlier. The depth of the groove, the height of the central bump, the distance from the center to the stable groove. All of these depend on the self-coupling strength. And that energy landscape determines the value the Higgs field settled into after the Big Bang phase transition. Change the self-coupling, and the field would have settled into a different value. Different particle masses, different chemistry. Measuring the Higgs boson's self-coupling is therefore one of the most important experimental goals in current physics. The Standard Model predicts a specific value for this self-coupling. If the measured value matches the prediction, the Standard Model passes another test. If it deviates, something beyond the Standard Model is affecting the shape of the Higgs potential. The challenge is that measuring self-coupling requires producing two Higgs bosons simultaneously from a single collision, a process called Higgs pair production. This is extraordinarily rare. Single Higgs boson production happens once every 10 billion collisions. Pair production is roughly 1,000 times rarer still. The Large Hadron Collider has collected enough data to begin setting constraints on the self-coupling, narrowing down the range of possible values. Run-3 data is pushing those constraints tighter, but a definitive measurement likely requires a more powerful collider or an enormous increase in data volume. Future proposed machines, including a potential future circular collider with a circumference several times larger than the Large Hadron Collider, list Higgs self-coupling measurement as a central scientific motivation. The boson that grants mass to the universe must grant mass to itself. That loop, that strange self-referential property, is the Higgs boson's deepest quirk. And it sits at the heart of a set of questions that modern physics cannot yet fully answer. The Higgs boson was found. The Standard Model predicted it. The prediction was confirmed. And yet the discovery opened more questions than it closed. The hierarchy problem remains unsolved. Nobody knows why the Higgs boson is as light as it is. Nobody knows what cancels the enormous quantum corrections that should push its mass to the Planck scale. Supersymmetry is unconfirmed. Extra dimensions are unconfirmed. The elegant mathematical solutions that seemed promising before the Large Hadron Collider switched on have not shown up in the data. The self-coupling of the Higgs boson has not been measured precisely enough to confirm whether it matches the Standard Model's prediction. The answer to that measurement determines the exact shape of the universe's energy landscape. It tells us how stable the Higgs field truly is. It tells us whether the vacuum decay scenario is real or irrelevant. Nobody knows whether the Higgs boson is fundamental or composite. Every measurement so far is consistent with it being fundamental. But every measurement so far is also consistent with it being composite at scales just beyond current experimental reach. There is no way to distinguish between these possibilities without reaching higher energies. Nobody knows why different particles couple to the Higgs field at such wildly different strengths. The top quark couples hundreds of thousands of times more strongly than the electron. The neutrino couples so weakly that its mass is almost nothing. The pattern of these couplings is confirmed but unexplained. No theory has successfully derived these numbers from first principles. Nobody knows whether the Higgs field is the only field of its type, or whether additional Higgs-like fields exist at higher energy scales. Some extensions of the Standard Model predict multiple Higgs bosons with different masses. None have been found. But the search continues, and at the deepest level, nobody knows why a universe with mass-generating fields exists at all. The Higgs mechanism explains how mass arises given the existence of the field. It does not explain why the field exists. The Standard Model describes what the Higgs field does. It does not explain what the Higgs field is at the most fundamental level, or why it has the properties it has rather than some other properties. These open questions are not evidence that science is failing. They are evidence that science is working. Every answer reveals the next layer. Every confirmed prediction opens the next set of testable questions. The discovery of the Higgs boson was not the end of a search. It was the beginning of a more precise one. The Large Hadron Collider continues running. Future machines are being proposed and designed. Theoretical physicists are exploring frameworks that might eventually explain the hierarchy problem, the coupling pattern, and the stability of the vacuum from deeper principles. Somewhere in that future data, in that future theory, the next layer of reality is waiting. The Higgs field fills all of space. It is pressing against every particle in your body right now. It has been there since a fraction of a nanosecond after the universe began, and despite everything physics has learned about it, the field still holds answers that no human has yet found. The most important particle ever discovered still has secrets, and the machines being built to uncover them will push to the absolute edge of what physics, engineering, and human curiosity can reach. The edge is exactly where science does its best work.